Okay, so we ended yesterday's lecture with Bayes' theorem, and we discussed how we can turn it into a way to determine a posterior probability density for a parameter, which is something that has no meaning in the frequentist approach. And we observed that we need to plug in something which is not defined by any external constraint. The posterior probability depends on the prior probability, which I indicate usually with pi. So we will use this notation pi often instead of p. And how can I choose prior probability? There is no basic principle. If you know nothing about a parameter, one way to describe your ignorance about the parameter is to set pi to a constant. But beware that if the range of definition of your parameter is not bounded, this prior may not be integrable. So integral is infinite. So an effective way to consider it is that maybe you can assume that if you have a parameter theta, let's say defined from 0 to infinity, this is a constant up to a certain cutoff, and then it goes somewhere to 0. This cutoff is sufficiently large, and if I multiply pi by a probability density which goes to 0 more rapidly than the cutoff, the result will not depend on the cutoff. It's sort of a regularization. So let's consider a concrete example. I take a Poissonian counting. So I imagine I have a detector and accounts some cosmic rays. So I count a number n of cosmic rays, and I want to know something about what is the rate, okay? So what I know is that the number of counts we saw yesterday follows a Poisson distribution. So the probability distribution for n given the parameter nu is equal to nu to the power of n e to minus nu divided by nu factorial. So what can we say about nu? We can build a posterior, and the posterior is given by Bayes' theorem. So P of nu given n is equal to what? The probability density, so this one, times the prior. And then the denominator is just a normalization constant. So we can put a constant here. Then we can determine a posteriori. And the constant is just the integral of this density. So if I put in a constant, and I play this trick, I say this basically is a constant up to a very large value of nu, but since we have an exponential term here, this dumps any possible, let's say, bad behavior at large values of nu. So in this case, we can say that this is proportional to nu to the power of n e to minus nu times a normalization constant. And if you do the integral, it turns out that the normalization constant is actually, again, n factorial. So if you compute the posterior is actually, it has exactly the same expression as the probability density, but here we have a probability distribution where n is the random variable and nu is the parameter. Here we have a probability density where nu is your random variable, and what is happening? No, Pierluigi Campana. We'll call him later. Maybe I switch to not disturb. Okay. So while this is the histogram we saw, well, actually you didn't see well last lecture because it was tilted and it was, well, so I fixed the images, but they are slow to move anyway. You know what is this distribution? I mean, yeah, exactly this Poisson. Okay, too slow. Anyway, this is a histogram which you should see somewhere. Okay, here it is. So this is basically a histogram as a function of n. This one is a function of nu, and if you plot it, this is a so-called gamma distribution. So if n is equal to 0, this term is not present, so this is just an exponential. So this is for n equals 0. If n is equal 1, 2, blah, 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 you start to have that the probability density is 0 at nu equals 0. So this is nu, this is p nu given n, nu given n. And then more or less the shape is like this, okay? With a given maximum. Note something interesting. If you observe n equals 0, the most likely value is nu equals 0. If you observe n different from 0, the value nu equals 0 is impossible. Because if you assume that nu is equal to 0, then you will always observe n equals 0. So as soon as you observe n which is different from 0, n nu equals 0 is an impossible value. So this gives you also a feeling of how Bayesian reasoning works. So you do some observation, and then this gives some probability density to the value, to possible values, which depend on how likely the outcome is. And if you observe something different from 0, the value nu equals 0 is just impossible. Now, what can I say? Imagine that we are in a situation where nu is different from 0. So the most likely value here, it turns out, if you compute the maximum of this function, you compute the derivative, set it equal to 0, and you see that this maximum is set to nu equal to n. So the most likely value is this one. What can I say if I want to put some uncertainty about this, this value? What I can say is this. So this is the posterior PDF, this is nu, and this is P of nu given n. This is the most likely value. And then I can define an interval with a content, for instance, of 68%, the 1 sigma Gaussian level, and say within this interval, so if this probability is 68% or 68.3, if you want to be more precise, this may be my uncertainty interval. So how can we set this interval? Again, there are different possible intervals, all having 68%. So I can have extreme cases where I say that this is 68%. In this case, I have an interval which is from 0 to an upper limit. I can have another extreme case where I take this curve and the interval is from a lower bound up to infinity. Or I can decide to take something in between. So one way could be, for instance, to set the area, if this is, I call alpha, I set this equal to, or maybe better, this is 1 minus alpha. I set this equal to alpha divided by 2. So I have different, I have 2 tails which have the same area. This is one possibility, but beware, consider the first case. I observe n equals 0. If I observe n equals 0, what I get is a negative exponential. And if I use this trick, I basically cut some area on the left, some area on the right, and I remain with this interval. And the most likely value is 0. So in this case, the most likely value lies outside the uncertainty interval, which is not really pleasant. One way to overcome this problem is to find the shortest interval. And one can demonstrate, I mean, the demonstration is not difficult, but takes a bit of time, but you can try to do it yourself, and you can find it online. That if you take a curve like this, and you cut by a horizontal line, this defines an area here, 1 minus alpha. And you can tune the level of the horizontal line. So this may be another interval. You can decide to move this horizontal line in order to have 68% contact. This procedure gives you the shortest possible interval. So the interval with the smallest distance between two extremes. So basically, you can say that if the probability density is equal to, at the two extremes, x1 and x2 are identical, then the interval x1, x2 has the minimum size. And this also works for this case because you cut basically at the horizontal line where you have a 68% content here. And you end up with an interval from 0 to the upper bound. This is one way. Okay, now I have an exercise for you. Let maybe cancel this exercise. And maybe you help me solve this exercise. So imagine I want to buy something online, okay? So I go to eBay, Amazon, whatever, and I say two different sellers. Seller number 1 has 100% of feedbacks, and seller number 2 has 97% feedback. So which one would you pick? So is more reliable seller number 1 or seller number 2? Number 1. But then you look closely. This has a number of positive feedback, which is maybe, let's see, no, I don't know if I have, yeah, imagine this has 8 positive feedback on a total of 8 positive feedback. But this other one has 97 positive feedback over 100. So this has a longer experience compared to this one. Now, can we say something about who is more reliable? Who would you trust more? So one possible answer comes from Bayesian inference. So these are a number of feedbacks which are positive over a total number of feedback. So imagine that the seller has, let's say, a standard uniform with time probability to receive positive feedback, okay? So what distribution follows this number of positive feedback? So I have a number of feedback, which is number of positive feedback, and the total number of feedback, okay? So this is fixed. This is the number of items that the seller has sold online. This depends on the probability of positive feedback P, okay? So what distribution is it? Binomial, perfect. So you can imagine that the probability to have n positive feedback given P and capital N is equal to the binomial coefficient P to the N, 1 minus P to N minus N, okay? And then now we can reverse this using Bayesian inference. So what is the probability distribution on P, okay? So we can say that the probability density, posterior density on P, given the number of observed feedback in N, is equal to, now we do the same trick. So we have a constant. This is also a constant because this contains N, which is a number which you have observed. The only variable is P, okay? So it's a constant times P to the N, 1 minus P to N minus N, and then you have the prior. Now, what we put as prior? We could put a uniform value from 0 to 1. P is bound to be between 0 and 1, okay? So it's okay. Or maybe we can look at the average seller, which is on eBay or Amazon, and we consider that distribution. So a priori, we don't know what to put. So the simplest calculation is if we set this to a constant, okay? And in this case, we have a posterior, which is just a constant that is a bit harder to compute, but again, it contains just some factorials, so it's nothing magic. And then we have p to the n times 1 minus p to n minus n. And let's see how this distribution looks like, if it is not too slow. Here it is. So the distribution for the 8 over 8 is this red curve here. And the distribution for the 97 positive case is this one. So it is true that this is not 100% reliable, but it's very unlikely that its reliability is below, let's say, 90%. Here instead, since we have a small number of cases, there is a good chance that this guy may be not as reliable as it appears. So maybe if we want to be conservative and we want to reduce the chance that we have some, let's say, unpleasant outcome, maybe we can put a cut here, and we decide to discard the first one because this guy has not enough experience, okay? So this is interesting. It's not intuitive, but it's something that you also, I mean, tend to reason this way, but without rationalizing this too much. So how can also we formalize it? Now, you remember yesterday we said that the binomial distribution is just a binomial process is just the sum of capital N Bernoulli processes, okay? So here we can consider something that is also true not only for this case, but also when we consider the experimental data. So if we take a prior for a given parameter theta, imagine we have a number of independent measurements that we do. For instance, we do collision events, or we collect cosmic data, or we wait for neutrinos from some source, and so on. Our likelihood function of our sample, which is made of a number of observations, given some parameter, this is equal to the product of a probability density for xi given theta, okay? If those are all independent events, okay? This is how the likelihood function can be written in terms of independent probability density. This is something which you have already encountered this? I guess, I think so. So our posterior is just P of theta given x1, xn is equal to a normalization factor times the likelihood times the prior. But this can also be written this way. So we have k, then we have probability of the last, let's start from the last one, just for convenience. P of x n minus 1. So you see, what you're doing here is you start from your prior. Then you do the first observation, and you have, let's say, the posterior number 1. Then you consider the posterior after first observation as prior for the second observation. And then you basically build a posterior number 2, okay? Then, so on. At the end, you have the posterior number n, which is basically obtained taking as prior the posterior, which you obtain considering all the sample except the last one. So you can consider Bayesian inference, and this works except, I mean, up to a normalization constant, which you can compute every time by doing an integral. So you can see that Bayesian inference is a sort of learning process. So every bit of information which you add allows you to change from your initial prejudice, which is something that may change from you to you and so on, and then you move to something which is different. And now let's see how this can apply here. So we start from pi of p, which is a constant. Then this should be multiplied by p if positive p, if the feedback is positive. Or times 1 minus p if the feedback is negative. Okay, so what are these probability density? P from 0 to 1, this is the positive feedback, and this is the negative feedback. This is p, this is 1 minus p, okay? And this is what you have to multiply to. And what we get, what do we get? Here is what we get. Here I started from two different priors. So on the right side, the prior is the prior is the yellow line, you see? Here I started from a constant prior. Here I start from an exponential prior, okay? So if I start from this one, I get a sample here of, let's say, randomly extracted feedback, which are ordered. So I have a positive feedback, then a negative one, positive, positive, negative, and so on. And every time I have to multiply either by p or by 1 minus p. So what I get here, I start from the yellow one, and then I move to the one which are more darker. And I start from the yellow curve. Then you see they move, and they reach something which is close to the true value, which is 0.7, if I remember correctly. And what you notice here is that if you start from this curve or this curve, the more information you add, the more the posterior is insensitive on the prior. So in this sense, if you have enough information, Bayesian inference no longer depends on your prejudice. And why? The reason is the following one. The posterior is equal to the likelihood function times the prior divided by the normalization factor, okay? Now, if you have enough information, and this x is a sample of many observations, as a function of theta, this likelihood function will be a very peaked distribution, okay? Because there will be just a small interval of the parameter theta close to the value where this has the maximum, okay? Where this is non-null. If my prior is, let's say, sort of smooth function, okay? Within this short interval, maybe I put in different color, yeah. The shorter is the interval, the more you can approximate the value of the prior to a constant. And if it is a constant, you have here at the numerator, at the denominator you again have the same constant. And if this is a constant, this can be brought outside the integration, and they cancel in the ratio. So if you have a short interval where the likelihood function is significantly different from 0, your prior will no longer matter, unless your prior is pathological. For instance, imagine you have a prior which is, I don't know, a spike around 0 and then 0 for all other values, and then you enter into contradiction. So in that case, if your prior is too strongly polarized, this may mean that you have something like a religious belief in something that is observable. When the observation contradicts your prejudice, you enter into some contradiction. Okay? So reasonably, we will never put priors which are too strongly constrained, and hopefully, if we have enough information, we will not have this strong dependence on the prior. Now, there is just one last thing that I wanted to mention, and then we move to frequentist inference.
May I ask what happens if the prior is another experiment?
Sorry?
If the prior is another experiment, and
yeah,
this is strongly disagreeing with you.
Exactly. This, in that case, you have two measurements which disagree, and you have the same. As with the frequentist. If you want to combine two measurements that do not agree, you have a problem, and you have to do something to mitigate the disagreement. So either you relax the uncertainty, which means that you relax your prior. Okay. Okay. Last thing, and then we move to something else. So we have another way to define well, maybe I'll do an example before we move to this definition. So imagine we want to measure some particle lifetime. So I have a number of measurements T1, Tn of decay time of a particle. So we measure many decay times. And then the likelihood function is the product of many exponential terms. And even every exponential term is just 1 over tau e to minus t over tau. So if I do the product of the different term, what I should do is just put t sub I here and do the product from 1 to n. Now, the issue is that you have two different models. You can have either tau here as parameter, or you can have lambda, the inverse of tau. And in this case, you have times lambda, okay? Now, what is your prior? Should I put prior pi of ti equal to constant, or pi of lambda equal to constant? So which one is most natural? There's no preferred parameter. So maybe the particle width is important, but maybe also the lifetime is important. So in these two cases, if this is a constant, you can easily demonstrate that dp over d lambda is equal to dp over d tau times d tau over d lambda. And since they are one in absolute value, and this is proportional to 1 over lambda square, okay? Instead of being a constant. And by the way, this is not normalizable. So unless you have something which dumps here the prior, you may be in trouble. So if we expand this, how can we write this? This is just lambda to the n e2 minus the sum over I of ti times lambda, okay? So if we multiply by 1 over lambda square, you need to have at least 2 measurements. Not, otherwise, you have something which is divergent, okay? What is the posterior? There is another way to define the prior, which is called the Jeffreys prior. I will not enter into the details, but if you define something, maybe we can find time to look at this more in details, but just wanted to mention you that this can be partially mitigated if we define a prior of a parameter which is defined as square root of the determinant of a matrix called Fisher information, and this is this matrix is defined as the expected value of the second order derivative. So if this is a matrix, so we have j parameters, okay? So we have this is a vector of parameters. This is the expected value of the derivative, the derivative or the logarithm of the likelihood function by theta I derivative of the likelihood by theta j. I don't want to enter into this detail. If you do this definition, whatever parameterization you use, you end up with something which has always the same expression. So I don't want to enter into the details, but in this case, the prior, due to this Jeffrey, for this case, is 1 over lambda, and is also equal to 1 over tau. So this is sort of invariant. So you basically, if you use this definition, whatever parameterization you use, the definition changes according to the Jacobian, and then you end up with the same definition in the new parameterization. So this is sort of invariant under reparametrization. But I don't want to enter into the detail. What is the, what is the posterior you get if you multiply by 1 over lambda square or 1 over lambda? Again, you see the posterior is just a gamma distribution. And the maximum here is, in the case you have a uniform prior, the maximum value is just the tau equal to 1 over n sum over ti. So the lifetime which gives you the largest probability, is the arithmetic mean of all the measurements. If you use the lambda minus 2, you end up with the, let's say, tau prime, which is 1 over lambda, is equal 1 divided by n minus 2 sum of ti. So you see the distributions are very similar, but the maximum, instead of being corresponding to the arithmetic mean, shifted on the right. So this is the prior, the uniform prior. This is Jeffrey's prior, the one which is invariant, proportional to 1 over tau. And this is the uniform prior on lambda. This is for n equal 5. But if you go to n equal 10, clearly the difference in the peaks, which here differs by 1 unit and here by 2 units at the denominator, is less, because, I mean, 10 minus 2 and 10 minus 1 are closer than 5 minus 2 and 5 minus 1, okay? And if you have 50, it's even more. So the more measurements you have, the more you are insensitive on the prior, okay? So this is basically the end of the story. So I would stop with the Bayesian inference now. Are there any questions about this, what we discussed so far? There is no physical meaning related to the prior. This is just a model of how your initial ignorance about this parameter can be described mathematically. So if I say, for me, initially, any possible value has the same probability, I set the prior to a constant. But then, which is the parameter which I should consider uniformly distributed? You see, in this example where we consider the lifetime, is the lifetime the parameter where, for me, every value has the same prior probability, or is the width the inverse of the lifetime, which has the same prior probability? So defining the prior in the correct way is an issue. Maybe should we consider the mass of a particle as the parameter we are ignorant about, or the logarithm of the mass? Maybe we want to use logarithmic series. So the problem with this, you see, this inference is very nice, very close to scientific reasoning, but we start from a prior, and there is nothing we can do about that. So that's why many consider unpleasant Bayesian inference.
Is there a way to quantify exactly how insensitive one is to the prior? Will they have an experiment and they have a number of measurements and they cannot change that?
I think the best way to do it is to run your analysis up to the final measurement, and then, for instance, you quote how much the final value and the uncertainty interval change according to the prior. So this depends exactly about what you do with this posterior distribution. So if you extract an upper limit, or if you quote a central value with some uncertainty, so I would run all the way through the end of the analysis and quote the different result depending on how much we reasonably change the prior. So if we want to be insensitive on some unreasonable prior, like the one I mentioned with peaks and so on, clearly we will see distorted final values. But if we take reasonably smooth priors, and we demonstrate that we are not much sensitive, then we can say that we are in a regime where the Bayesian inference is not sensible on the prior, and then we are safe. This one? This one is basically because here you have this term here. So this is lambda to n minus 2, e2 minus lambda sum. Okay, so you have to do the derivative of this quantity with respect to lambda, and you end up basically with a term n minus 2, which comes from the derivative of this guy. In the other case, you just have n. So you see, this is exactly the same expression. Here you have n, here you have n minus. Sorry. Here you have n, because here you do, this is equal to lambda to the n times e2 minus sum of ti times lambda. Okay. So here you have n, which gives you the denominator. Here it becomes n minus 2. More question about Bayesian inference?
Just a question about what's written after the G is E times delta times.
This is the expected value. This is a E with the, you know, this double line. And this is the expected line of the derivative of the likelihood function with respect of theta I. This is a matrix.
What is this function? Sorry.
This is the logarithm of the likelihood function. Sorry, this is, sorry. I wrote it very badly, sorry. Sometimes my hands move too fast. So the likelihood function is just the probability density for the data. And since this depends on the sample, you can average over many different samples. But I mean, let's not consider this too closely, because I mean you can find this on the books, and I don't want to spend too much time on this. Just wanted to mention you that there are different ways and different approaches to define this prior. Okay. More questions? So we shift to a different subject. So now we have, we saw before the law of large numbers, which allows us to define frequentist probability. So we say that we can consider a probability as the limit for an infinite number of random extraction of the frequency of the occurrence of the process we are looking for. And this allows us to determine a probability density which gets closer and closer to the frequency the more random extraction we do about our experiment. But so now we have a probability that can be associated to repeatable experiment. Maybe I stop it, otherwise we get distracted by this guy running. So how do we define an inference process in the frequentist fashion? So let me delete this on the Blackboard. So with the Bayesian approach, basically we can define a probability density for the parameter, but probability density for a parameter is something meaningless for a frequentist approach, because the parameter is not a random variable, and the parameter cannot be randomly extracted. So what can we say? From the frequentist point of view, I want to imagine an algorithm. So any algorithm that we will find the best algorithm that, given some observation x, allow us to obtain two things. One is a parameter, a value of the parameter that we call point estimate. And then, together with this, we have an uncertainty interval, theta 1, theta 2. Now, given x, which is random, this is an algorithm that we call estimator. Okay, so different algorithm will be different estimator. So once I have this random variable, I extract the point estimate and the uncertainty. And since this is a function, an algorithm, I mean, basically is a function, the point estimate and the extremes of the interval will also be random variables, okay? So if I do another experiment, I can repeat the experiment because I'm in the frequentist regime. I obtain different point estimates and different parameters. So what is the frequentist way to define that this interval corresponds to, say, 68% probability? So this doesn't mean that I assign a probability value to theta. This is nonsense in the frequentist regime. But I can say this. I can repeat the experiment many times. Since the point estimate and the interval are random variables, repeating from time to time, I obtain different values. And what I get is that sometimes the true value, which I don't know, is contained in the interval, sometimes not. You see, the red ones are the one where I miss the central point. So we have a coverage. Coverage is the word we use in the frequentist domain, we have a coverage of 68% if 68% of times in the limit of an infinite number of experiments, which we cannot realize, so we use it in a pragmatic way, if in 68% of the times this interval contains the true value that we don't know. So this is another example where I just extracted a bit more with the computer, and you see if actually this is what you get from a real random extraction. Now, one way to define an estimator is very easy if we have a simple probability density. So imagine I have a probability density for x which depends on mu and sigma. And imagine I know sigma, so sigma is known, but mu is unknown. So imagine I observe x, okay, or x equal x star, for instance. Then a way to determine an estimator which has nice properties is to assign mu hat just equal x star. In this case, what is the distribution of mu hat? And this is the probability distribution for mu hat. Well, since mu hat is equal to the extracted x, this follows a Gaussian distribution centered around the true value with a width which is equal to sigma, okay? Do you agree with this? And then what can I say? That if I define as interval sigma minus mu minus sigma, mu plus sigma, this interval contains the true value with 68% probability by construction. So, in this very simple way, I was able to, sorry, mu hat. I was able to define a point estimate and an uncertainty which is just equal to the standard deviation of the Gaussian, which have the proper coverage. Are there other algorithm that we can consider? Well, we can be inspired by the Bayesian reasoning, but
Luca,
actually
Luca?
the Bayesian, 1 hour?
No. Did you assume P was a Gaussian or you didn't?
The distribution is a Gaussian here. This
So
is a Gaussian,
you assumed
yeah.
it was a Gaussian?
I assume that this is equal to a Gaussian. Okay. I assume that this is a Gaussian. So we can either be inspired by Bayesian inference, or you can consider this independently. One possible algorithm is what we get from Bayesian inference in the case where we have a uniform prior, because if I have a uniform prior, you remember, from the Bayesian point of view, I have that the posterior for the parameter theta is equal to the likelihood function, actually, times the prior, but if the prior is a constant, it's just, I can just put it away, and then I have to normalize this. So what is the maximum value of theta? The maximum value of theta is the value that maximizes the likelihood function. So imagine I take as algorithm the given Ex, I take x hat equal the value which maximizes the likelihood function, okay? This is called maximum likelihood estimate, and this gives you the point estimate. I'm cheating here. It is not true that the maximum likelihood estimate is chosen because it is inspired by the Bayesian inference, because actually what we are considering is a number of properties of this estimator. So we want to have that the estimator is not just a random algorithm. So imagine I have a value x which follows some distribution. For instance, here I consider my Gaussian distribution. Imagine that I associate theta hat, which is always a constant, 4.5, okay? Is it a useful estimator? That gives me some information about the parameter? No, because if I randomly extract the value of x, this estimate does never change. So I can say that the expected value of theta hat is always 4.5, but I actually would like that the expected value of theta hat to be equal to the true value. So this property is called consistency of the estimator. So an estimator is consistent if, on average, the estimator is equal to the true value. If I have an expected value of the estimator, which is different from theta, and this is different from 0, the difference I call bias of the estimator. So I would like this to be unbiased. So this is not very useful because I mean this is gives me always the same value, does not even converge. Actually, I would like this to be true at least for n that tends to infinity. Okay, to n that tends to infinity. And the maximum likelihood estimator have an interesting property that the bias in particular may be present, but if it is present, this goes to 0. In proportional to 1 over square root of n. So if n is sufficiently large, the bias gets down. There is another interesting property of estimator that I want to study. And actually, if I have an estimator, theta hat, okay, whose distribution is nicely centered about the true value. If I have an estimator which is broadly distributed, this is less interesting than one which is as a narrow distribution. So I would like also the width of the distribution, the probability distribution for the estimator to be as small as possible, because a narrow distribution means better precision. If I then want to assign an uncertainty interval related to a 68% probability, I can assign a shorter interval to the narrow distribution and the broader interval to the broad one. So I'm actually interested in the variance of theta hat, and I would like to get it as small as possible. Unfortunately, there is no lower bound to the there is a lower bound to how small I can make this variance, because it is possible to demonstrate a theorem due to Kramer and Rao. And this theorem says that the variance of any estimator is greater or equal to an upper bound, and this is given by 1 minus the derivative of the bias with respect to theta hat to theta, yeah, squared. I think it is, if it is correct, yeah. So if you have an unbiased estimator, this term up the numerator is 1. But the denominator is the Fisher information which I introduced for the Bayesian inference, and I have here a minus the expected value of it is equal to the expected value of the derivative of the logarithm of the likelihood function by theta squared. Okay, and this is the Fisher information matrix you found, remember, with the Jeffreys prior. This can be also demonstrated to be equal to, if you change sign, it is possible to demonstrate that it is equal to the derivative of the bias divided by minus the expected value of the second derivative of the logarithm of the likelihood function. And we will use this quite a lot. So the variance is cannot be smaller than something if the estimator is consistent. Now, what can I say about this estimator here? What is the variance of this estimator? So I always have 4.5 as my estimator. What is its variance? 0. So here we apparently, the variance of this theta hat is equal to 0. So we violate Kramer-Rao bound, but we violate the Kramer-Rao bound because this is not a consistent estimator. So its average value for large number doesn't go to that doesn't converge to the true value. Okay, so what we can do with useful estimator, so this is useless estimator, is that you can never have arbitrary small variance. And a very nice property of the maximum likelihood estimator is that for maximum likelihood estimator, for n that tends to infinity, the variance approaches the Kramer-Rao bound. So basically, maximum likelihood estimators for large numbers are unbiased in the limit of large values and provide you the smallest possible uncertainty in the sense that the variance of the estimator is equal to the upper bound. Okay, so that's why actually we use most of the time maximum likelihood estimator. Now, how to determine the uncertainty? There are a number of ways to determine the uncertainty interval in order to provide this coverage. And there are, I show you first of all an approximate way. So if we say that the for large n, a maximum likelihood estimator is approximately unbiased, I can say that the variance is approximately equal to 1 over the minus the expected value of the second order logarithm derivative with respect to theta. And this could be approximated by the expected value could be roughly estimated as the second order derivative computed at the minimum. So it's 1 over minus logarithm computed for mu equal to, sorry, theta, we call the parameter theta equal theta hat. And this gives a formula which is very frequently used. What does it mean? If I take a Gaussian distribution, so I take, for instance, this one, okay, and I do minus logarithm of the likelihood function, minus logarithm of the likelihood function is what? Minus logarithm of this is 2 pi sigma square, right? Plus the logarithm of this guy, which is with the minus sign, I get this, I get rid of this minus, and then I get x, sorry, square is here, x minus mu squared divided by 2 sigma square. So if I do the second the second order derivative of this guy, okay, I get rid of the factor of 2, and I get that the variance is actually sigma. Okay, so for the Gaussian case, this approximation basically works this way. You have a Gaussian distribution. If you do the logarithm of the Gaussian distribution, So the Gaussian distribution is a constant. A quadratic term. So if I do minus 2, consider logarithm 2 gets rid of this term, of the Gaussian distribution, this is basically x minus mu over sigma squared. So you start from the Gaussian distribution, and you end up with a nice parabola, which has actually, it goes to 0 for mu, x equal mu, so I should put this here. And basically, when you read it as a function of mu rather than as a function of x. So we can put mu here, x is the minimum, and then do it depends on sigma, okay? So basically, you turn the Gaussian into a parabola with this kind of approach. So that's why we will very often use minus logarithm or minus 2 logarithm of the likelihood function. Here we use minus logarithm because with the double derivative, we get rid of the factor 2 here. It is a technical point. Okay. Now, what happens if I'm not exactly in the parabolic approximation? So what I can do to estimate the uncertainty is this. So if you are really into this regime, you could do the following. So you could take, if I take as value for minus 2 logarithm of the likelihood function, if I set the value equal to 0, I get the minimum, okay? If I put here 1, when is this minus 2 logarithm of likelihood equal to 1? This means that mu minus x squared divided by sigma squared is equal to 1, which means that mu is equal to x plus or minus sigma, okay? So these two values here are x minus sigma and x plus sigma, okay? And this is a nice way to define the uncertainty interval. So basically, what you can do this. You can take the likelihood function. You don't know if it is Gaussian or not. You may assume that it is close to a Gaussian approximation. And then you draw minus 2 logarithm of the likelihood function, whatever it is. So maybe it's not exactly Gaussian, it does something like this. The minimum may also not be exactly at 0. So here it is in the, let's say, in the exact case of a parabola. Maybe we are not getting exactly there. And there are cases where you never get there. So maybe you are at this level. So the minimum gets you the, we call the parameter theta rather than mu, okay? Theta hat. And then you consider the value at the minimum plus 1. So when you add plus 1, you have two values, which are theta 1 and theta 2. Now, what is interesting of this approach that you may get asymmetric errors. So if this is the negative error, so is, let's say, delta theta minus, and this is delta theta plus, this may be not exactly equal as you have in the case of Gaussian approximation. In this case, what you quote? You quote theta hat, theta is equal to theta hat plus delta sigma plus minus delta sigma minus. And we already saw that you could have asymmetric intervals with the Bayesian approach, so this is not a surprise. The only thing is that this needs to be taken with a bit of care. So these are two approximate methods. There is also a way to make this in a more rigorous way, but we will see this after 5 minutes break. So we can take a break. I can also answer questions if you have. Va bene? Va bene. Come tempo, fammi vedere quanto mi manca. No, anche come tempi non ci sono, non è male.
Abbiamo preso uno 2 volte il logaritmo di
Mhm.
quel fattore di 1 su radice.
È una costante, è vero.
Che
Sì, ce
assomare
l'ho tolta, ce l'ho tolta. Sì, ho detto che questo è uguale a questo più una costante che ho messo. Sì, 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 sì. Scusatemi, certe cose a volte le riglisso un po'.
Forse l'ho perso io mentre
No,
scrivevo.
no, può darsi. Sto rivedendo il video, mi mangerò le mani. Guarda. Prego. So your colleague noted that I should have added the constant here, okay? Because there is logarithm of 2 pi, okay, anyway.
Ma quindi alla fine la likelihood è soltanto il prodotto delle PDF dei
Se,
dati parametri.
se i dati sono presi in maniera indipendente.
Certo, poi ovviamente
Se ho la ripetizione di un esperimento tante volte e ho tante misure, cioè tante collisioni, tanti raggi cosmici, tanti neutrini, sì. Se io ho parametri invece che possono avere delle correlazioni, delle cross
è la
dipendenze,
PDF
no.
congiunta.
E quella a quel punto è quella congiunta.
Però è soltanto un altro modo per chiamare la PDF congiunta.
Esattamente, esattamente.
Ah, ok, però
Cioè,
è solo una roba che non
sì,
mi
nel caso cancelliamo una cosa che non
adesso
c'era
noi
prima.
abbiamo due variabili che sono correlate, no? Cioè una PDF congiunta con un fattore.
Quella PDS, esattamente, a quel punto
È
non la
la stessa
fattorizzo.
identica
Stessa cosa,
cosa. Si
esattamente.
chiama solo un modo diverso.
Esattamente, cioè quello sarà l'IQ di XY dati i parametri di θ.
No, esattamente.
Ah, perfetto, ok.
Più avuti di-
Sì. Ah. I have one more wrong. Okay, I can just do this by hand. I missed one image.
May I ask something? Is a very dumb question. Here, shouldn't it be swapped or is this right?
No, here you have the likelihood function is the distribution, the probability
Yes.
distribution for the data given the
Yes.
parameter.
Yes, so
You,
this
you
is
swap
given,
it,
right?
yeah, this is correct. You swap it only when you compute the posterior in the Bayesian approach. So if you put, if you write P of theta given X, this is a probability distribution where you assume that this is the unknown variable.
Yes.
And this is only meaning in the Bayesian approach.
Yeah, okay.
Here in the frequentist approach, we never talk about this because,
Okay.
because theta is not a random parameter.
Okay,
So we
okay.
take the likelihood function, which is the probability density for the data,
Okay.
and we take the maximum value of this one.
All right. But this is not
Maybe,
varying,
no, no,
right?
okay, so this is the superior, maybe the notation is not correct here. This is not maximum value of the likelihood. This is the value which maximizes
So
theta.
this is X, right?
No, sorry, I have to fix it. Yeah, this is not correct. So this is the theta which maximizes the likelihood function. So you have the likelihood function,
Okay.
and this is the value of theta that maximizes the function.
Oh, okay, okay.
Sorry, I wrote something incorrect. So thank you for making this. So, okay. So thank you for letting me notice this. I wrote something which is not correct, so sorry, and maybe this, I will ask the guy who is mounting the video to fix it. So I wrote something like this, okay? This is not correct. So this is just wrong. Sorry, I had in mind something different. So this is not the value, the maximum value of the likelihood. This is the value that maximizes the likelihood. So if I take the likelihood function as a function of theta, okay? So this is the likelihood function as function of theta. Theta hat is the value which maximizes. So how can I write it? Argmax is, what is the right, is it correct? Argmax, argsup, something like this. Is it correct? I don't know, I'm not, is this correct? Probably, so this is not correct. I should have written this one, sorry, okay. Apologize for this. And I asked the guy who will mount the video to put a warning sign after that. Okay. So, so maybe we can consider an example which we already took under the Bayesian approach. So how do we measure the lifetime of a particle if we measure the decay time of n particles? So we write the likelihood function. And this is equal to the product of the probability density for each of one, because these are independent measurements. Okay? And this likelihood function is equal to 1 over tau to the power of n, e2 minus sum over I divided by tau. And then we have to find the maximum of this function. So how do we find the maximum of this function? We set the derivative equal to 0. So we do derivative of L equal to 0. And we end up with an equation, which, I mean, I don't solve it, but it's tau equal 1 over n, sum from I equal to 1, from 1 to n, ti. So we can estimate it as the most probable value in the Bayesian sense where we had a uniform prior. Okay? Now, what happens if I use lambda instead of tau? Here, I obtain the same result. Because something nice of a maximum likelihood estimate is that this is invariant under reparameterization. Because if I change the parameters here, the maximum doesn't change if I just change parameterization. And this means that this property is, of course, different compared to the Bayesian one. Now, something that I can compute is the uncertainty associated to tau, and I can compute the variance of tau hat, actually. This is the estimate, okay? So this is 1 over n, the sum of the variances. Sorry, 1 over n squared, right? If you take the variance, multiply it by a constant, and this is the sum of the variances, so it is n times sigma. Sorry, the variance is the variance of tau. If I have an exponential distribution, the variance of the exponential distribution is equal to tau. This is a general property of exponential distribution. So here, what I end up, tau, variance is tau squared, sorry, the standard deviation is tau. So I end up with this being equal to tau squared divided by n. And so the standard deviation is tau divided by square root of n. This is, one can also demonstrate that this is equal to the Kramer-Rao bound, okay? Now, what happens if you have more measurements, like in this case? Another result which is very easy to determine, I don't show it to you, is that if you have the product of n Gaussians, okay? So if you have x1, xn, and they all follow a Gaussian distribution with the parameters mu and sigma is known, you end up with the maximum likelihood estimate for mu, which is equal to 1 over n times the sum of xi. So it is the arithmetic mean. And you also end up with the estimate of sigma square, which is 1 over n sum from I equal to 1, from 1 to n, of x minus mu hat, xi minus mu hat squared. And one can demonstrate that this has actually a bias, but the bias is decreases as 1 over n. And indeed, the unbiased version of this is sigma hat squared unbiased is equal to 1 over n minus 1 sum of xi minus mu hat squared. Okay, this is how to correct the bias, and clearly you see that for a very large n, 1 over n and 1 over n minus 1 are basically the same. Okay. Now there are cases where your likelihood is defined for more parameters, so you may have more parameters. And in that case, the model which approximates the likelihood function to the Kramer-Rao bound is a Gaussian distribution in more dimension, where you may have a correlation term. So if you multiply two Gaussians and you have e2 minus x minus, let's say, mu x square divided by 2 sigma x square, and you multiply by the equivalent term where you have y minus mu y squared divided by 2 sigma y squared, okay. You can multiply the two and put the denominator in the exponential in common, and you end up with something which is x minus mu x squared plus y minus mu y squared divided by 2 sigma y squared, okay? If you imagine that you can do a rotation between these two variables, so you start from xy and you consider a rotation here by some angle phi, what you find is that this quadratic expression ends up containing a non-diagonal term. So this is proportional to this. You get something which is x prime minus mu x prime squared divided by 2 sigma x prime squared plus the same but you end up also with a term which you don't have in case of the simple product of two probability. You have something like x minus mu x times y minus mu y. And then you have something which is, how to put this, 2, let's call it sigma xy prime, okay? So with plus or minus, this is a matter of convention. So you end up basically that in 2 dimensions, if this equation, so if you set that this is equal to some constant, describe an ellipsis which have axis oriented along x and y, this other equation will give you ellipses which are oriented in a tilted direction. Now, I don't enter into these details, but what is interesting to us is that if we have a likelihood function that is a function of more parameters, so you have a likelihood function of some observables, and then you have parameters theta 1, theta 2, okay? You can take minus 2 logarithm of the likelihood function, and you will end now in a situation where you have 2 dimensions, okay? So in 2 dimensions, you can maximize the likelihood. So you find argmax and so on, so not what I wrote before. And this means that you have to minimize minus 2 logarithm of the likelihood function. So the parabolic shape is now in 2 dimensions. So how do you represent it? What we can see in 2 dimensions, I mean, it's very hard to represent it if you have theta 1 and theta 2. And you have minus 2 logarithm of the likelihood function. This would be sort of paraboloid in 2 dimensions, but what we can do, we can take the minimum at some point, which correspond to a given theta 1 and theta 2, and then we start to cut it the same way we did with the 1D case. In the 1D case, we had the minimum, and then we cut at values which are plus 1, okay? And we could do the same. So if we take a plane where we have the minimum plus 1, this will cut a curve, which if you project on the 2-dimensional plane, like a minimum, you may end up having an ellipsis, okay? And again, we can approximate the quadratic form using the second derivative terms, so we can do this. We can consider that the covariant matrix, which is the term which occurs here, so you can write the term, the quadratic term in this way, so you can write, let's say, xi minus mu I times xj minus mu j times vij to minus 1, okay? This is a generic quadratic term. V to minus 1, the inverse of the covariance matrix is minus second derivative of the logarithm of the likelihood function with respect to theta I, theta j. And this is inspired by the Cramer-Round bound. and is very close to the real uncertainty if n is sufficiently large. And if you compute the inverse of this matrix, so you end up with this V, you have a form which in two dimensions is just sigma x squared, sigma y squared, and here you have sigma xy, okay, where you have the off-diagonal term that appear in the term here. Maybe the notation is not exactly correct, but so this is the correct notation here. The upper one is probably not 100% consistent with what I wrote. So, how do you interpret an ellipsis in this space? So, if you cut this at minimum plus 1, this means that if you project this on a one-dimensional histogram, this interval is an interval in theta 1, so you have theta 1 min, theta 1 max, will have a 68% probability content, a coverage in this sense. If you project on the other interval, you end up with another interval in the second parameter where you have 68%. You may also take projections into other directions. For instance, I take this slanted projection, and here you have a 68% probability on an axis which is, let's say, tilted compared to the other one. Something which is worth noting is that the area here, if you take a Gaussian two dimension, and you take the area of this 2D ellipses, is not 68%, but is much less. It is 39.4%. So in some papers, you see that they quote delta log likelihood equal 1 contour, and this means this. In some papers, you see that you have 68% contour. And if you want 68%, in this area, you don't have to cut at 1, but you have to cut at, let me check the table, 1.51. So if you enlarge this, because you cut it at, 1.61 squared, I believe. Yes. Because, why do we need to do square? Because if you have minus 2 logarithm lambda, the minimum is your estimator. If you add plus 1, you get plus or minus sigma. If you add plus or minus 4, if you add plus 4 from the minimum, you have minus 2 sigma plus 2 sigma, because here this is a parabolic shape. Okay, so we need to have delta lambda, delta logarithm of the likelihood function equal z square, and z is the number of sigma you want to compute. So in this case, if I put a contour at minimum plus 1.51 squared, so is z equal to 1.51, I get this 68% contour. So there is, be careful when you read the content of your paper, because in some cases you have delta lambda equal 149, because you have to go squared. In some other cases you have 68%, 95%. And some paper quote both. So it's a bit tricky. Many give this, let's say, as don't specify too much, so you have to be careful when reading it. Okay. Let's consider another interesting problem, which is shown here. Unfortunately, I didn't manage to put this in the right way, but I will draw this for you in a better way. So how do we measure peaks with maximum likelihood estimators? So the problem that I want to discuss here is how we measure the yield of a peak under some curve which overlaps with some background. So what you should see here, if you rotate your head 90 degrees this way, I draw it for you. Sorry, this is again. So imagine I have some reconstructed quantity, typically mass or energy, where I expect that a signal is a sort of monochromatic value, okay? This is the mass of a particle that I'm interested in. Now, if I have a finite resolution of my experiment, or if the particle has some intrinsic width, instead of having just always the same value, I expect to have something with some distribution here. Now, this distribution is a Bright-Wigner in case there is some resonance, but let's consider the simplest case where I have a very narrow width which is intrinsic to the particle, and I'm dominated by the detector effect. In this case, what I expect is basically a Gaussian distribution where the sigma is the resolution of your detector. Now, imagine that I observe not just signal, but there is some background. And now, on top of this signal, I have some background. In this plot, I made a random exercise with computer, and the background is just an exponential. So here, I have E2 minus lambda m. And lambda is just a parameter that tells me how steep is the slope of the background. It's nothing fancy. And here I have the central value, which is I call mu, okay? And the sigma is the width. Now, if I sum the two, what I end up with something like this, okay? How does this turn out in real life? In real life, I have a number of points, M1, M2, Mn, and they are distributed in part according to the background and in part according to the signal. So what is my probability model? I have to make a mixture of two probability distributions. So if this is, maybe I use two colors. Why don't we take advantage of these chalks? So the signal is red. Can you see the colors? Maybe not too well. Okay. So I have a probability function for the background, PB, which is lambda E2 minus lambda m. And the probability distribution for the signal, which is PS, equal to the usual Gaussian. So what will be the distribution for the overall sample? So there is a given probability to end up here and a given probability to end up there. What is the probability to end up in the signal? So the probability to end up in the signal region is just F sub S equal the signal yield divided by the signal plus background yield. And the probability to end up in the background is B over S plus B. Note that F sub S plus F sub B is equal to 1. So what is the probability distribution for the two? I can just put the two together. So I have P of M equal to Fs times Ps of M plus Fb Pb of M. Okay. And what is the likelihood function that I can build for this model? It's just, since I have many independent measurements, I can write a likelihood function that is the product of many of these guys. So, my probability density is equal to, M1 Mn is equal to the product of PMI, which is product from I equal 1 to n f sub s ps plus f sub b pb, okay? I can do something more. Do we use here the information that the total number of entries is n? No. But this is an important information because n is also a random variable. N is distributed according to a Poisson distribution. And I can use it to constrain the value of s plus b because n, the expectation value for n is equal to s plus b. And I can use this information, plug it in another term. So I build up what is called extended likelihood function. So the random variables here are m1, mn, but I also take into account that the number here of measurements is equal to n. And the random variables are signal yield, background yield, and the parameters which appear in the likelihood function. So for the background lambda, and for the signal I have mu and sigma, for the signal. And this is equal to the probability distribution for n, which is a Poissonian term. So I have e to minus s plus b to the power of n factorial, times this term here, product. We can do a little bit of math just for fun, but I will not go too much further here. And we can write this in this way. So we have e to minus s plus b divided by n factorial. I have s plus b to the power of n, and then the product gives me product from 1 to n of ps is just s ps of mi plus b pb of mi, and I can put at the denominator s plus b, okay? So s plus b multiplied n times simplify with this term. So if I take minus logarithm of the likelihood function, it gives me s plus b plus the sum s ps of mi plus b pb mi. And this is something that I have to minimize. Now, we cannot minimize this analytically. Well, there is also logarithm of n factorial, but so you have minus, so you have plus logarithm of n factorial, but this is a constant term, does not depend on the parameters which I want to minimize, so this is irrelevant for the minimization. The way we minimize this is usually numerical, and the most common algorithm use what is called gradient descent, and you have, I'm sure you are familiar with minuit and all the minimization which you may have used in your career, I guess. So we end up with an estimate of the signal yield, the background yield, and so on. Here what we did is we considered the each individual measurement to be it alone a piece of information. Clearly, this method can be applied, but imagine n is, I don't know, at LHC we have samples which are order of 10 to 9 events, and so on. This becomes impractical. So in practice, this unbinned maximum likelihood, so this is called actually unbinned extended maximum likelihood, because we extend the likelihood with this term. So this is what, and then use the single individual measurement. Here, for display purpose, which is just, miserable because this was turned by this Mac to Windows conversion, I displayed the data entries as histogram entries You see, for every bin, I put some number of entries just for display purpose. But in the fit, I'm actually using the individual value of each single mass measurement. So I don't consider any binning in this distribution. Binning is inconvenient because if you start with the sample from whatever large amount of data, you reduce the number of information to the number of bits, which could be, I don't know, 100, maybe 1,000, but usually not more than that. Okay, and this we will consider later on how to do this, but you can already have in mind an idea. Yes?
I'm not sure what SNB are.
SNB are the expected signal and the background yield. So the number of expected signal event and number of expected background event. This is something that we determine from the fit, yes. These are unknown parameters. These are parameters that define basically a Poisson distribution. Okay, this may fluctuate. So the actual number of events from signal and background may fluctuate. Okay, so this is what you expect from the theory point of view.
So the unknown things are
SB, lambda, mu, and sigma. So these are what you determine from data.
And this procedure you just outlined allows to extract all of them?
If we perform a minimization with the minuit or any other kind of minimization algorithm, you find the minimum in 1, 2, 3, 4, 5 dimensions. Okay? And then if you select 2 of these variables, you can obtain contours in 2 dimensions. Okay? So here it's hard to visualize contours in more than 2 dimensions. In 3, you have something which you have to rotate on the screen. Okay? Yes, something that we can do, and we'll discuss at the end of this lecture, I hope. But we could, if you wish, I can also anticipate this. If you have this distribution, you see that where you have this background plus the peak, imagine you have a very large number of entries. In this, you have, I don't know, 1 million entries. Computationally, this product, or the sum, if you compute the logarithm up there, may be very expensive because you have to evaluate a Gaussian or an exponential 1 million times. So what you can do, you can divide this into a number of bins. They may be of equal size, but also of different sizes. And then what you're interested in at this point is not the exact shape, but what is the expected number of entries in each bin, okay? So the expected number of entries in each bin, I can call hi, is equal to the integral extended over bin I of the PDF, okay? So in this case, it's P of M. And for short sides of the histogram, we can approximate the function to be a constant. So this is approximately P of M times the delta I, the sides of the bin. Okay. So how do you build a likelihood here? If you wish, I can anticipate this. The number of events in each bin follows a Poissonian distribution where this is the expectation. Okay, so I have the probability distribution for the observed Ni is actually equal to a Poisson distribution given Hi. And Hi is in turn a function of all these things. Sum, signal, background, mu, lambda, sigma, okay? So, in this case, you can write either the likelihood function as the product of Poissonians, which is something that is feasible in some cases. And this is done because actually you have this is just an exponential distribution. The logarithm is something that can be computed. But more often, instead of writing explicitly the Gaussian, the Poisson distribution, one approximates the distribution as a Gaussian. And the variance of the Poisson distribution, you know that the variance is equal to hi. So this is the famous estimate that you may have that the expected uncertainty you have, the expected standard deviation here is square root of hi. So the sigma I is square root of hi, okay? In many cases, instead of using the square root of okay, how do we build then a PDF in this case? This is just a Gaussian, and this is just -2 logarithm of the Poissonian distribution is up to a constant, is just ni minus hi divided by hi all squared, okay? And if I do the product of many of these terms, I end up with the sum of this term. And this is the so-called chi-square variable, so I anticipated you something that I wanted to show you later on. So what you minimize here is the sum of quadratic terms. Well, all these hi may depend on the unknown parameters, okay? And may depend just because they are equal to the size of the bin, which is a constant, and then you have the PDF basically, which approximates the number of counts, because you have to integrate this over a short interval, but you approximate this to be a constant. Okay, so in this case, in many cases, you may end up in this so-called binned likelihood case. And these are the most common histogram fits that are performed in particle physics. This is something very common. And all so the model is very simple. It's just a quadratic term. In some cases, you also approximate the denominator with the, instead of putting hi, the expected number of entries, you put the observed number of entries. So in some cases, you can put here n sub I. And this is a reason why we set an error on each measured point. This is not correct, strictly. The number of observed points is something that is exactly equal to what your detector measured, but we assign an error in the sense that this is an estimate of how much is the expected yield. So the point here is the exact measurement we get for data. When we set the error, we say that this is the error if we interpret this as the estimate of how much is the yield in that bin. Okay. Now, okay. So I anticipated this binned part. So if you are curious, okay, maybe I can skip this, it takes too long. So now I want to move to a different topic. So far we have considered approximate way to determine uncertainty for our parameters. Now let's move to the first principles, and let's define, at least in theory, because this is not always considered as effective way to determine uncertainty, but if we don't want to rely on the approximation that okay, maybe let's just recap what we did so far. So we consider two ways to determine the uncertainty. Or we say that the variance matrix, the covariance matrix -1 is equal to minus the derivative of the likelihood function with respect to the parameters. Okay? Or we take -2 logarithm of the likelihood function, we scan it, we find the minimum, and then we set minimum +1, and we determine this uncertainty, okay? We say these are approximate way because this relies on the Kramer-Rao bound. This relies on this sort of parabolic approximation. That in case we don't have a parabolic shape, gives us the asymmetric uncertainty. Now, if we take this as approximate method, what would be the exact method? So let's consider the simple case of one dimension and one variable. So imagine that I have a probability density for x given theta. How can I construct an interval which has exactly the coverage I want? So what I can do is the following. Here I take x, and here I take theta. So imagine I scan the value of theta from minimum to maximum value, and I take a particular value, theta 0, okay? What can I determine here? Here I determine, for given value of theta 0, the probability distribution corresponding to this value. Okay, so I have something like this. Now, what is my point estimate? So my point estimate is the value which maximizes here. So I can say that here is the most likely value. And then I have to decide how to quote an interval at 68% probability. Okay, so this is 68%. Now we have different way to do this. You remember, either we take the fully asymmetric on one side or fully asymmetric on the other side to determine upper or lower limit, or we take equal areas on the two tails, or we take the shortest interval, or we do whatever we want. So we have some convention. This convention is called ordering rule, which measures how extreme values should be discarded, okay? So this is a way to determine how to discard the tails or one of the two tails. Now, we get an interval here, okay? And then we repeat this to another value. So we take another value here. Maybe the most probable value is somewhere else, and maybe the interval is somewhere else, okay? And then we do this again and again. Okay, so we end up with a number of these intervals. If we are lucky, this will be sort of smooth, and all these intervals will form basically a band. So if I put together the curve made of the extreme values of these intervals, I end up with two bands. Now, imagine I build up this band from theory. Imagine that I observe a particular value, so I take another color, and I measure this value. This is x observed, x star. So what I can do, I can build up a vertical line, and this vertical line cuts the band at two extreme values. I can also consider, of course, the point estimates here, okay? So this band, imagine that there's also some point estimate. So the interception of the point estimate line gives me the point estimate for the parameter, and this is just the best fit value, the most likely one. And then I project here the uncertainty interval. So if I do this construction, I'm guaranteed that by varying these because of random fluctuations, the interval will also vary, okay? And since I've put a 68% content on the horizontal histogram, or the horizontal intervals, I'm guaranteed that the vertical interval that are defined in this construction have a 68% coverage, okay? This is called Neyman construction, and gives us an exact coverage. So if we don't trust the approximation given above, which are valid in many cases but not always, we can be more, let's say, can be more rigorous in the definition of the uncertainty. So this is the construction you get, and this is also what you find in the particle data group. Now, imagine the very simple case where I take a Gaussian. And in case I have a Gaussian distribution, well, the interval is very easy to construct, because if this is x for a given mu, the interval will be just, if I take mu, then the most likely value will be equal to exactly mu, and then the interval will be 1 sigma wide. Okay, so I have taken sigma equal to 1. And all the points will lie on the diagonal, and the two bands will be just 1 sigma away from the diagonal. So if I build the vertical interval given an x star, this will be just mu hat equal to x star plus or minus 1 sigma. Okay, so here there is nothing trivial. Something which is maybe a little bit more tricky is if you consider a binomial distribution, because we end up with a bit of problems, which I want to outline you in the last 8 minutes that we have. So what do we do if we have a discrete distribution? Now, let's take, for instance, a binomial distribution. For a binomial distribution, how should I proceed? If I take in this case, how much did I take? N equal to 10. Okay, so my random values of n could be from 0 to 10. Okay, so I can go from 0 to 10. And what are the probability distribution? Imagine that I take a given value of p. Now I have to build an histogram here. I just build it randomly. I don't trust that this is exactly the binomial distribution. Okay. So here I have probably p, which is probably very close to 0.3. Okay. The most likely value is 3, is this one. And now how do I build a 68% interval? Unless I'm very lucky with the choice of the parameter, there will not be a precise way to define an interval that contains integer values that exactly guarantees the coverage I expect. And how can I proceed? So I can take, for instance, a tail on the left and a tail on the right, and start to exclude values until, let's say, next exclusion will give my probability below 68%. So I want the interval to be short. If I take the interval too large, I get a probability which is 100%, which is too much. I start to take out extreme bits, and I stop until the integral under this area, maybe put the h on the other side. So this probability is greater or equal to this 1 minus alpha, equal to 68%. Okay. So there are again different ways to define this interval. You can put extreme intervals on the two sides, but you are not guaranteed to have a coverage which is exactly 68%. So the coverage is 68% or more, so it's at least 68%. This construction is based by an algorithm due to Klopper and Pearson. So they exclude the tails where the probability to have n, let me copy the exact value because otherwise I may get something worse. less or equal to k given n and the lower limit is equal to alpha divided by 2. So what do? I take the tail until this has a probability content no more than alpha divided by 2. So instead of guaranteeing this, I guarantee the opposite. So I take the, I'll do, maybe I draw a different histogram here. So I start to let's take one histogram. Okay, it's not exactly the same histogram, but imagine I start from the right side. I start to add bins, and I stop where this area P tail is less or equal to alpha divided by 2. In this case, if I take one bin more, I exceed alpha divided by 2. So take the largest interval from the right, which takes out from the interval which I want to select alpha divided by 2. In this way, I can build this construction here, which is very interesting. And you see that while the central the point estimate are very easy because you just take p hat equal n divided by capital N. Okay, this is the central estimate, and I didn't even draw. These are points which are on the diagonal line. So 0 is 0, 1 is 10%, 2 is 20%, and so on. So these are just points on the diagonal. You see that the intervals may be asymmetric. Here in particular, it's fully asymmetric. The interval goes from 0 to an upper bound. Okay, and here instead is very symmetric because it goes from 10% is here, but the interval you see is very asymmetric. If you go to central values, it's more symmetric, and then it gets the opposite on the other way. Now, what is interesting on this is that you can study varying p. Here p is the true value, and you don't know. You can measure which is the coverage, because if you vary p, you change this histogram, okay? And when you change the shape of the histogram, you can measure the coverage, because you can compute the expected, the fraction of time. If you run many times your random extraction, you can compute which is the effective coverage if you know the true value. And what you end up is something like this. So if I move p from 0 to 1, you see I would like to have 68%, but if I have n equal to 10, I have this very funny ripple structure. In particular, if p is equal to 0, and this is something which is very unpleasant, but it is the case. So if p is equal to 0, I have that the only possible histogram is 0, and 0 probability. So with 100% probability, I have 0. And with 0 probability, I have the rest of the values. So whatever interval I do, this will cover with 100% probability. So there is no way to exclude this value, and you get something which is basically all the interval you get, whatever interval you set, this will always contain the true value. So there will be no chance to exclude the true value. And this is something a bit unpleasant. If you increase, by the way, the number of entries, you see you get closer to the expected value in the central region, but at the extreme, you still have this strange thing. Okay, I think I'm done for today, right? And so what I tried to show you is that you may end up in some problems in case of discrete variables. And so even if you, while on the Bayesian side you are dependent on a subjective prior, which is unpleasant, on the frequentist side, if you use properly the confidence interval is the name for the Neyman construction, for discrete variables, you end up in intervals which don't guarantee the coverage which you desire. So both have problems. So no, life is not perfect, okay? And we will see more on the next lecture.
So just a reminder, we resume at 2 with the other lecture, and then there is a discussion following the other lecture at 4:30. Okay, thanks.
And if you have any question before I disappear, you can ask now or maybe next time we meet.